So in this class, we will take up a design problem of a flat slab with drop panel and column head. In the last class, we have designed a flat slab with only drop panel, without column head. So here I will consider a circular column. So column size is 5 mm diameter and panel size same 6 meter by 6 meter as the last problem. Live load and finished load also I have taken the same value 3 kN per meter square and 2.5 kN per meter square, and materials also I have taken same M25 concrete and AP 4 steel. So here this is the additional portion, this column head, this is the additional portion. So if they ask you to provide this column head also for the flat slab, then the thing is the reinforcement will be reduced, because whatever load acts on the column here, so that will be distributed. That will be distributed over this area of the column head, and that is why the load on the column will be reduced, which finally gives economical design. That is, you can have less reinforcement. So in that case, let us see how we can design the flat slab along with the column head. Now here, in this case, the first thing is we have to assume the diameter of this column head. So first step, assume diameter of column head. So normally the diameter is taken, D is taken as 0.25 times L. So 0.25 times L, it is the diameter normally we assume. So 1/4 of L. L is 6 meters. It means that is the panel size. So 6 meters means 6,000 mm. So if you multiply this, I think you will get 1,500. So diameter of the drop panel. So this is your diameter. That is column head. Diameter of column head. So this is your D. From here to here. This is your. Okay. So that is it. Of course, it won't come from here. In this sketch, you can take somewhere from here. Okay. Yes. So this is your diameter from here to here. So you can assume that as 0.25 times the panel size. So that means you have in plan, so the column head looks like this. So this is the diameter. This is in plan 1,500. So naturally the what we can say that critical section for the punching shear case, it will be like this at a distance of D by 2 from the outer face of the column. So this distance will be the D by 2. This I have explained in the last video itself. So here what was the value of D there? They have taken 249, because it is same problem. So D is 249 divided by 2, it comes to how much? 124.5. So your total diameter now, your total diameter will be, so 1,500 plus 120 plus 249 only. D by 2 this side and D by 2 this side. So it is 1749 mm. This is the total diameter of the critical section. So this is the critical section for punching shear. Okay. Now, what we have to do here is, normally the circular section is considered as an equivalent square section. So, see, circular section is transformed or considered as an equivalent square section. Equivalent square section. So if you want to find the diameter of that a particular circular section or the square or side of the square section, the meaning here is, see, this is the circular section. This I am going to convert into a square section, so that the areas remain same. So area of the circular section, area of square section, they should be same. If I take the side of the square as A here, so I have to find out this A value. So the diameter of the circular section here is 1.5. So I am converting this column, circular column, into a square column of equivalent equal area. So this here the diameter is 1.5 meters. So we are converting, to give circular column, we have to convert that circular column into equivalent square column. So here we have to equate the areas of this one, and you have to get the value of A. So if you get the value of A, that is the square column size. So what is the area of the circular column? Pi by 4 into d square. Okay, pi by 4 into 1.5 square. This should be equal to A into A, that is A square, correct? Area of square. So what is the value of A from this? I think you get 1.33 meters. Size of the square column is 1.33 meters. 1.329, which you can take as 1.33. Now here we are going to calculate that what is the value of LN, clear span. LN is the clear span. So there we have taken clear span as, in the last problem we have taken clear span as 6000 mm minus 500 mm. Here we have to take the square this clear span as 6 minus 1.33. This is what we have to take. So now this becomes, that means what we are doing is we are treating that column head, circular column head into equivalent square column head. That's all. So this is actually the column head. So we are transforming circular column head into square column head like that. So 6 minus 1.33 becomes 4.67 meters. This is the value of LN. LN is the clear span. Then what we have to do is we have to calculate the load coming on that panel. So or the column head, capital W. So this capital W is nothing but WU into L2 into LL. So same formula whatever we have used in the last lecture, same formula we are using. WU is how much? Last problem 18 point something we got,
56.
18.56 is WU, ultimate load. Into L2 is 6 meters. Into LN is 4.67. So this value you get in kilonewtons. This is the equivalent concentrated load acting on the column head. 520 kilonewton. So for that we have to calculate the bending moment. So this is the load. So this is step 1. Second step, calculate bending moment. So bending moment we have to calculate using this formula. Mu is equal to, what is the formula? W into same formula, Ln divided by 8. Same formula, whatever we have used earlier. Same formula. So W is 520 here, Ln is 4.67 divided by 8. Here the value of Ln is different compared to the earlier value.
303.5.
How much?
303.55
kilonewton. So this is the moment, bending moment coming on that. So in this, the negative bending moment, positive moment you have to distribute. So negative bending moment, we know that it is 65%. Positive bending moment is 35%. As per the code. So negative bending moment is 65% of mu. That is 0.65 into 303.55. Positive bending moment is 35%. That is remaining. So it is moment is distributed. So 0.35 into 303.55. So get the values. First value is
197.3
kilonewton meter. So this is the negative bending moment. Positive bending moment. So remaining thing.
106.
106.25.
Ah, sir.
Yes. So we have to then these are the negative and positive. Next, out of this, one more step is there. Your design moment will be 0.75%, 0.75 of this and 0.6 of this that I have given as per the code. So final moment will be like this distribution of moment. So final design moments after distribution. So negative moment will be, in this we have to take 75%. So that is 0.75 into 197.3. That is your negative bending moment. So it comes to 148 kilometer. And positive bending moment is 60%. That is 0.6 times 106.25, which comes to
63.75.
63.75. 63.75 kilonewton meter. So please note that these two are the moment values for which we have to design the column strip, and we have to design the this is for the column strip. Please note, this is for the column strip. So in the column strip, moment will be more. If you take the middle strip, so whatever balance moment is there, that will be taken care by the middle strip. So balance moment means, so for the middle strip, negative bending moment will be equal to, so whatever total is there, that is how much? 197.3 minus this 148. Got it? That is for that we have to design the middle strip. So what is the value?
49.3.
49.3 kilonewton meter. Similarly, positive bending moment will be this value 106.25 minus this 63.75. The value will be
42.5.
42. So these are the final moments. So just like in the last problem, whatever we got, that is 4 values of moments we got, we designed 4 reinforcements, assuming 12 mm diameter bar. So we have designed 4 reinforcements. So these are the values of the bending moments we have to take for the design of reinforcements. So we have to design 4 reinforcements here. Now, what we will do here is, so before going for the design, we will check whether the depth provided is sufficient or not. So check for depth. So third step. So after calculating the bending moment, we will check for the depth. So whatever depth we have provided, whether it is sufficient or not, we will check. So for that, what is the formula we have to use? Same formula. Check for depth. Last problem what we have done without column head. D is equal to mu by
0.1.
mu by 0.138
138 FCK into B.
FCK into B.
B root.
Yes, whole to the power of 0.5 or
Root.
root of that. This is the formula. Okay. Now mu is the higher of these four values. Please note that. So highest value is 148. Among these four, whichever is highest, that we have to take. So it is 148 now. 148 into 10 power 6, because I have to convert to Newton millimeter, divided by 0.138 into FCK is 25 here, M25 concrete, into B is 3000. Please note that the column strip E and middle strip both have 3 meters length. So column width of column strip and middle strip width is 3 meters, that is 3000. So same value we have taken last L by 2. So L is 6 there, 6 by 2 is 3 meters. So 3000 mm. So what is the value of this D?
120.
120. So required, this is actually required. D required is 120 we got. But what is D provided? D provided is 249.
Yes. Yes.
So safe. So this is greater than 120, therefore safe. So this check we have to do. So automatically for the higher value, if you check all the other values, definitely it will be satisfied. So whatever depth we have provided is okay. That is the meaning. Now we have to check for punching shear. Fourth one, check for punching shear. Check for punching shear. So this procedure is similar to what we did in the last problem. So only thing is, what is the diameter of the critical section here? So I have shown in the last sketch. So dia of critical section is how much? 1500 plus 249.
Yes.
Plus 249. So that is 1749 mm. So this is the diameter of the critical section, or you can write it as 1.749 meter. Correct? Diameter of the critical section is that much. What is the perimeter? Perimeter of the critical section or circumference. You can write perimeter or circumference. Usually in square sections we call it as perimeter. In circular section we call it as circumference. Perimeter of critical section is nothing but circumference formula pi into d. That is pi into 1.749. What is the value? Pi into d.
5.49.
5.49 meters. 5.49. Now what we have to do is, we have to calculate the shear on the section. We have to calculate, that is VU. VU value we have to calculate. So what we did in last time, we have deducted that area of the column, this thing, the critical section area from the total area. So here also we have to do like that. So shear on this section, I will write shear on this section. Shear on this section, VU is equal to so what is the load? 18.56. So 18.56 into area. Area, what we have to do here is, it is 6 into 6 minus, it is circular now here. So what is the diameter of the critical section here? 1.749. So we have to take pi by 4 into 1.749. So this is the square, pi d square by 4 formula. So this is the answer for V. That is the shear coming on that. What is the value? You will be getting in newtons. you will be getting it directly in kilonewton, not in meter. Directly you will be getting in kilonewton. Because the load is in kilonewton per meter square and this will be in meter square. Then we will calculate the nominal shear stress to be
623.
625. Nominal shear stress to be is given by Vu divided by, here we have to take that perimeter into depth, perimeter into diameter. So here it is like this. So perimeter into that 247 whatever is there, that is the width, 249, because it is treated as a rectangle. So circular, if you convert to rectangle, instead of this thing, for circumference we have to take, multiply it by that 249. So what we are doing here is, so this I have already given this sketch. So here, this is how it is. So this actually is d by 2, is it not? So you have got column like this. So you know that this is 1.5 meter diameter, okay, or 1500 mm, and this one from here to here total is 1.5 plus that 249, that is 1.749 meter. Is it not? So when you are calculating punching shear, so we have to take this panel. Panel is of size 6 meter by 6 meter. This is 6 meter by 6 meter, like this. So what we have to do is, this total area is 6 by 6, okay? In that we have to deduct this much area. This area we have to deduct. So remaining area will be only this. That is what is this area. Okay, total area minus this area. So now Vu is 625. So 625 into 10 cube, because I need in newtons, divided by perimeter is how much? Perimeter I convert into millimeters. So 5.49 means 5490 into 249. This is in millimeter square. So just simplify this, you will get the value of stress in Newton per mm square. So we value
0.45.
0.45. 0.45. I think same value we got, similar, nearly same value we got in the last case also. So now as per class 3163 of IS 456, IS 456, which we have used earlier also, we have to compare this value of tau B with tau C. So tau C is Ks into 0.25 root FCK. Ks into 0.25 root FCK. So here once again this Ks value, I have given the page number. Last design page number 14. Ks is 0.5 plus beta C. Same thing, 0.5 plus beta C, but it should be less than 1. Here beta C value is 1, so therefore it becomes 1.5, but since it will be less than 1, Ks becomes 1. So therefore tau C is equal to Ks is 1 into 0.25 into root 25. FCK is 25 here, M25 component. So that is the value. 1.25, correct? Yes. 1.25 Newton per mm square. So this is the shear strength of concrete actually. Tau C is nothing but shear strength of concrete. So you can see here tau C is greater than tau V. When tau C is greater than tau V, no shear reinforcement is required because concrete itself will take the shear. If you get tau V greater than tau C, then you have to design the reinforcement for shear. But normally in slabs, as already told, shear is not a main criteria. But anyway, we have to check for punching shear only if the load is more like machine load is there. So static load, machine load is suppose if they keep a machine just above the column. In such cases, loads will be more. Then you may have punching shear also. Then we have to design the shear reinforcement for the difference value. So some shear is taken by concrete out of the total shear. So for remaining shear, you have to design the reinforcement. In this case, since the concrete itself is taking all the shear, you need not design the reinforcement for shear force. So there is no need of shear reinforcement here. Next last step is we have to design the reinforcements for all the four moments, whatever we have got. So design of reinforcement. Fifth step, design of reinforcement. Fifth step. So here also we have to design reinforcement for four moments. Four moment values, correct? Column strip as well as middle strip. In column strip we have to design negative moment and positive moment. So there will be four things here. First one is column strip. Column strip. In that we have to design the reinforcement for negative bending moment. Okay, this is the first case. What is the value of mu? So you have to calculate mu by BD square. Now you can use SP16. See, go to SP16. What is the page number? Page number you can note down. For FCK 25 grade. For FCK 25 grade, you have to refer the chart. So directly you get the percentage of steel. From percentage of steel, you can calculate the AST required. So directly you can do that. So please note that B value is here 3000 and for the column strip D value is 249. These two things are you have to keep it in mind. And the value of mu is 148, I think, correct? 148 kilonewton meter. That means you have to take 148 into 10 power 6 Newton millimeter divided by 3000 into 249 square. So this is the value of mu by BD square. Page number is to do. What is the page number?
49.
Page number 49. FCK 25. That is for FCK 25. And FY forward. For these two, we have to see what is the decimal you will get.
0.795.
0.795. So from the table, whatever is given in page 49 of SP16, we just directly read out that PT value. If you don't get, you have to interpolate. Approximately, you have to interpolate and tell.
0.231.
0.231%. So this is percentage of steel required. From this you can calculate the AST. So AST is PT divided by 100 into B into D. So this is the AST value. Okay. So PT is 0.231 divided by 100 into 3000 into 249. Yeah, just simplify this. You will get in millimeter square.
1725.5. 725.5.
Okay, and 726. So from this AST, you need to calculate spacing. Okay. So how do you calculate spacing? S is equal to spacing of the bar. Spacing of the bar will be dia of one bar. So assuming 12 mm dia bar. So your AS will be 5 by 4 into 12 square. It comes out to be 113 millimeter square. Correct? 113 millimeter square. So you can calculate the spacing now. So S is equal to, spacing is equal to area of one bar divided by total area 1726 into what we have to do, into
Distance.
that length, span is 3000. So we are providing reinforcement for 3 meters width of the that is column strip. So what is this value?
196.
196 mm center to center. Say 190. Slightly you can reduce this. So this is how the reinforcement is calculated. This is the negative reinforcement. Note that negative reinforcement is provided at top. Similarly, we can calculate the reinforcements for all the other three moment values. So column strip, positive bending moment. For that we have to calculate. For that, what is the value of moment you have to take? We have to take the value positive bending moment in column strip is 63.75. Correct? So naturally, the value of bending moment is less. Therefore, reinforcement required also will be less. So you can assume even 10 mm diameter bar also. You need not go for 12 mm always. You can assume 10 mm also. If you assume 10 mm, so maybe your spacing, a little bit more spacing you will get. So just I will give you, so for the second value, you can just check this. Positive moment in column strip. So second reinforcement, column strip, positive moment, bending moment. So this is provided at the top, at bottom. At bottom, this is provided. So we have to design the reinforcement for M is equal to what is that? 63.75 kilonewton meter. And of course, your B and D value remain the same. B is 3000 mm, D is 249 mm. There is no change in that. So if you calculate MU by BD square and you use the table, so finally I will give 10 mm dia at 230. You can just check this. So AST 10 mm, you can assume 10 mm because the moment is less. At 230 mm center to center. You can provide this. Next, what is the third one? Middle strip. Come to middle strip now. In middle strip, you have to go for negative bending moment. Once again, it is called top of middle strip. The value of MU you have to take for this is how much? What is the value of MU you have to take?
49.3.
49.3 kilonewton meter. That should be converted to 49.3 to 10 power 6 Newton mm. When you are calculating the MU by BD square. Here B is 3000, but D is different. Please note that for the middle strip,
189.
D is different because the drop is not considered there in the middle strip. What is the value?
189.
189. So that 60 mm difference is there. 249 minus 189 is 60 mm, which is the drop. The drop will not be there in the middle strip. Drop will be there only in the column strip. Okay, so these values you have to take, and we can assume 10 mm dia bars because the moment is less. So 10 mm at 290. 10 mm at 290. You can just check this. Mm center to center. And lastly, middle strip positive bending moment. Middle strip positive bending moment at bottom we have to provide. So here, what is the value of MU we have to take?
42.5.
Still less. 42.5 kilonewton meter. Of course, B is same 3000 mm. D is 189. For middle strip, the effective depth is less. If you calculate the reinforcement, 10 mm at 290. So these two are same, of course. These two will be same. 10 mm at 290. Because the moment is less. Now, one thing we should keep it in mind. There is a restriction on minimum reinforcement. So minimum still is 0.12%. Please note that in any case, in any of these four cases, if you get, so minimum reinforcement is 0.12%. So 0.12% is 0.12 divided by 100 into 3000 into 215. Gross area we have to take. So 0.12 divided by 100 into 3000 into what is the total depth in the of middle strip. For 189 we have to add 26 mm. Overall depth we have to take. So that is 215. So this is your minimum speed. So what is the value of this?
774.
772. Actually, this we have to provide. This we have to provide. Actually, if you do, what happens here in the second case, that is in the here, sorry, not in the second case, in the third and fourth cases, 774. Last case, actually you are getting less. That means, in other words, if PT is less than minimum reinforcement, then provide minimum reinforcement. Correct? That's right. You have to provide minimum reinforcement. Actually, so here the first one, no problem. You are getting more than this 774. AST value I am talking. After getting PT value, you have to get AST value. That AST value is greater than this. Second one also it is greater than that. Third one also it is greater than that. But in the fourth case, because the moment is less, you are getting AST as some 675 something. In this case, 675. So if you compare this with this minimum value, so this is less than the minimum, correct? Less than the AST minimum. Then in that case, we have to provide this. That is why these two values are same. This and this they are same. We are providing the same reinforcement. So if you are getting the AST calculation less than the minimum, then you have to provide the minimum reinforcement as per the code. So I have written here top and bottom. If they ask you the sketch, I have already posted that sketch. So just you have to show some lines. So please note that in a flat slab, whether they give drop or both drop and column head, so the design procedure remains the same. Only thing is, if they ask you to provide a column drop, then additional thing is we have to check for punching shear by taking into account the column head diameter. That's all. That is it. So this is how the flat slab is designed.